Dear students, welcome back to CAM and follower. Already we have seen the various types of CAMs, various types of CAM motions of followers, then various types of CAM profiles according to the motion of the follower and the type of the follower. But as far as the manufacturing of CAM is concerned, if you see the profile of the cam, when you design the cam with specified type of velocity or acceleration, it has specified contour, and in this case the manufacturing cost induced is very high because it has to be manufactured very precisely with a special tools. Hence, in general practice, such type of cams are avoided. Only in case of special machine tools, we use specialized designs of cam profile. But in general practice, we use some other cam profiles which we are going to see in this lecture. Now, many times the cams with specified contour like circular cam or tangent cam are used, and such follower motion in such cases is determined. So we are going to see under this chapter the various types of cams like tangent cam with roller follower, circular arc cam with flat face follower, and eccentric cam with flat face follower. Let us start with tangent cam. Now what is tangent cam? So as you have seen, the cam have the base circle. So in this case there are two circles. One is the base circle of cam and second is the base circle of nodes. So this is base circle of cam and this is the circular arc of the nodes. And if we complete this circle, then we can say that there are two circles in this cam, and the profile is generated by the lines which are tangent to these two circles, that is base circle and node circle. So this type of cam is called as tangent cam. Let us understand some of the terms used in this case. So this is nodes, this is the base circle, this is the pitch curve which traces the center of the roller follower, this is the radius of roller follower. Then these tangents, this tangent here and here, that is the tangents on both sides, are called as flank. Then this total is called as cam profile. Okay, so this is the cam profile. So such type of cams are used for operating the inlet and exhaust valves of internal combustion engines, and these cams are usually symmetrical about the center line of the camshaft. Okay, so we can see this is the symmetrical about the axis and center line. Under these topics, the tangent cams are of three types. One is tangent cam with straight flank, second is tangent cam with concave flank, and third is tangent cams with convex clamps. So we flank, where now this is the flank. So this flank, when it is straight, we can say that tangent cam with straight flank. Sometimes this may be this type of structure. So this is called as concave cam, where it will go inside, and when this flank goes outside, then it is called as convex cam. Okay, So we are going to see under this topic the three types of tangent cams. Now it becomes important to analyze the cam because we need to find the velocity, acceleration and displacement of follower at any position on the cam profile, right? So we need to understand now the velocity, acceleration and displacement. In before to this type of cam, we had first find out the velocity, acceleration and displacement, velocity and acceleration, and then we had computed or the drawn the profile of cam, right? But here we have drawn the profile of cam first, and we need to find the velocity, the displacement and the acceleration of follower at any instant of time when it moves on the surface of cam, right? So here we are interested in analyzing these cam profiles. So before going to analyze, let us understand the basic terms which we are going to use in this case. Okay. Let us start with radius of base circle of cam. So R1 is the radius of base circle of cam. R2 is the radius of roller of follower, and R3 is the radius of nodes. Okay. Then alpha is the semi angle of cam, semi angle of action of cam or angle of ascent. Now here the alpha is shown somehow incorrect. Let us correct it. Here I take the pen, and now this actually alpha goes up to this, and this is the angle subtended. So this is alpha. So when the cam moves on the profile, roller moves on the surface of cam, we can see that when the point of contact is at E, the roller follower do not have any displacement, but as it moves ahead, the displacement goes on increasing, and up to this point H, the displacement goes on increasing, and the angle turn during this is called as semi angle of action or angle of ascent, right? Clear? Now this is alpha. Next term is theta. Now theta is the angle turned by the cam from the beginning of the roller displacement. Now we are measuring this angle theta from point E to point P. So and again from P to E. Now we know that from P to E there is no follower displacement. So in this profile, on this profile we can say that cam do not have any displacement, any velocity, any acceleration. But when it moves from E to P in clockwise direction, then the follower have some displacement, some velocity, some acceleration, right? Clear? So this is the angle theta we are going to measure in between E to P clockwise. Clear? Then phi is the angle turned by the cam for contact of roller with straight flank. Now here we should note that the surface of flank is straight, whereas the surface of nose is round. So when the follower have motion on the surface of flank, it obeys one equation, whereas when it moves on the surface of nose, it follows different equation, or it have different behavior towards its displacement, velocity and acceleration when it turns on nose. So we need to analyze the cam separately, analyze the follower motion separately on the surface of flank and on the surface of nose. Clear? So here angle phi is the angle turn by the cam during the motion on the surface of flank. So when roller moves on the surface of flank, phi is the maximum angle turned by the cam, right? So we can see here that the displacement starts at point E, and as the roller moves ahead and contact reaches to G, the roller is going to follow this flank profile of flank, right? So the angle subtended, if we see, then it is nothing but the angle between OB and OD. So this is zero displacement, and total displacement is nothing but equal to OD minus OB. Clear? Therefore this angle between OB and OD is called as flank phi here. Okay. Then omega is the angular velocity of cam. So that is okay. Now there are two cases. One, already I have discussed, there are two cases. One, when the roller has contact with straight flank, and when the roller has contact with nose. So we are going to discuss separately the analysis of motion of follower on the surface of flank and on the surface of nose. Now coming to the follower motion on the surface of straight flank. Here the displacement or the lift or stroke of the roller when it moves on the surface of flank can be determined as the movement from its lowest position to any point C. Let us say theta is the angle turned in between the 0 to phi. Okay, so phi is the maximum angle turned during the cam rotation on the surface of flank. So now theta is any angle in between 0 to phi. So let us say x is the displacement. So now if we consider that the roller reaches to position C from B, angle theta is the turn by the cam, and the displacement of the follower will nothing but equal to OC minus OB, right? Now OB is the minimum or the lowest position of follower, and it moves up on the surface of flank, and when it reaches to C, it attains some displacement, and the difference of this length, that is difference of OC and OB, is nothing but the displacement of displacement of follower, right? Therefore if we say x is the displacement, therefore displacement x is equal to OC minus OB. Now OC in this triangle, now if we see this triangle, that is BOC, this is a right angle triangle here, and theta is the angle measured at this corner, then OC is the hypotenuse, and if OC is the hypotenuse, then we can say that cos theta is equal to OB upon OC. Therefore, OC is equal to OB upon cos theta, right? So we write here OC is equal to OB upon cos theta minus OB. So moving ahead, if we take common OB common, then taking the denominator as cos theta, the equation becomes OB is equal x is equal to OB into 1 minus cos theta upon cos theta. Now if we see OB is nothing but equal to R1 plus R2, which is R1 is nothing but the base circle radius of cam and R2 is the radius of follower. Therefore, the total distance OB is equal to R1 plus R2. So into, if we want to find x, then it is R1 plus R2 into 1 minus cos theta upon cos theta, right? So here, as the angle theta increases, displacement increases. Here we can see that cos 0 is 0, therefore displacement is 0 at position when theta is 0, means at position B, and when it reaches to maximum position at D, the displacement is highest, right? And that displacement will be nothing but R1 plus R2 into 1 minus cos of phi upon cos phi, where phi is the maximum angle turn on the turn by the cam on the surface of flank, isn't it? So in this way we get the displacement of follower on the surface of flank by this equation. Now in order to find the velocity, we need to differentiate the displacement of the follower with respect to time. Therefore we can say that velocity is nothing but rate of change of displacement, that is dx upon dt. Now x is the function of theta. As x is the function of theta, this can be written as dx upon d theta into d theta upon dt, right? Now differentiating the equation of the above equation, we get the velocity is equal to omega, that is r1 plus r2 sin theta upon cos square theta into d theta by dt. Now d theta by dt is nothing but omega, therefore velocity is equal to omega into r1 plus r2 into sin theta upon cos square theta, right? So differentiating the above equation, we get the velocity of the follower on the surface of flank. Now if we observe this equation of velocity, we can see that omega is constant for the cam rotation, r1 and r2 is also constant, therefore the variable is only theta, right? Now as the theta is 0, if we put theta is equal to 0, therefore sin 0 becomes 0. So as the value of theta increases, the value of sin theta increases and cos square theta decreases and the velocity increases. So as the value of theta increases, velocity also increases, and the velocity is maximum when theta becomes phi. Therefore the maximum velocity is at the angle turn theta equal to phi. So when theta is equal to phi, the velocity is maximum, that is when it just leaves the flank. When the roller moves ahead from flank to the nose, at that position the velocity is maximum, and velocity is 0 at theta equal to 0. Okay, now let us find acceleration of the follower on the surface of flank. So acceleration can also be computed by differentiating velocity with respect to time. Therefore acceleration is equal to dv by dt, and already we know that the velocity is the function of theta. Therefore we can write it as dv by d theta into d theta by dt. Now differentiating this equation, we get acceleration as omega square into r1 plus r2 into 2 minus cos square theta upon cos cube theta. Okay, so this equation we get in order to find acceleration of follower on the surface of flank. Therefore if we observe this equation properly, again only theta is the variable. These three variables like omega, r1 and r2 is constant. Therefore only theta is the variable, and if we put the value of theta equal to 0, then the acceleration here cos 0 is 1. Therefore the value of numerator is lowest and value of denominator is highest when theta is equal to 0. As theta goes on increasing from 0 to some value, say phi, then it's any value in between 0 to phi, the theta goes on increasing from 0 to some value, and when we put some value here, the value of numerator increases and denominator decreases, and we can say that acceleration increases as the follower moves or roller moves ahead from BE to G, right? So from position for the center of roller, we can say that when the roller center moves from B to D, the acceleration increases, and the acceleration is maximum at theta is equal to phi. Therefore the maximum acceleration can be computed as omega square into r1 plus r2 into 2 minus cos square phi upon cos cube phi. And as the minimum acceleration is at theta is equal to 0, this value is nothing but becomes 1. Therefore the minimum acceleration is nothing but omega square into r1 plus r2. So in this way we can find out the displacement, velocity and acceleration of follower at any angle theta in between 0 to phi on the surface of flank of the cam, right? So here we have analyzed the follower motion on the surface of straight flank. Now coming to the next analysis, that is the follower motion on the surface of nodes. Now when the roller moves on the surface of nodes, it have different motion than on the surface of flank. So let us understand this more in detail. Before going to analyze, let us go through some of the terms which we are going to use for the analysis. Here, now angle measured by the angle measured during the cam rotation and follower motion on the surface of nodes is nothing but the angle theta 1. Now angle theta 1 is measured from J to D. So if we see, the angle phi is the maximum angle turn during the follower motion on the surface of flank, and angle alpha is the angle of ascent, so that is the angle of semi-angle of ascent, and theta 1 is the angle turn semi-angle turn during the follower motion on the surface of nose. Now we have seen that when follower moves from the surface of fan to the surface of nose, it say it is at point G when it turns moving on the surface of nose. Okay. So when it moves ahead and reaches to point, so G is the point where roller of the follower have contact with nose, and roller moves ahead on the surface of nose, and the displacement is maximum at point H, right? So the roller have contact with cam profile at point H. So if we see the pitch motion on the pitch curve, then the roller moves from point D to point J on the surface of nose when displacement increases, right? And the angle measured in between D to J is theta 1. But theta 1 is not measured from D to J, but it is measured from J to D. Okay, that you will understand from the equation why it is done so. So theta 1 is the angle here between OJ and OD, measured anticlockwise from J to D. Here now r, small r, is the distance of between the two centers, that is center of base circle of cam and center of nose. So the distance between the two centers is assumed as, say, small r. R3 is the radius of nose, and L is the distance between R3, that is L is the distance between K and J, that is center of nose and the center of roller of the follower. Okay. So in that case, the displacement x is given by this equation, that is x is equal to L plus R. Now you know that x is maximum displacement, x is equal to R plus L. So it is measured in opposite direction. So that's why theta is measured in anticlockwise direction. So maximum displacement is L plus R. Now as theta moves from J to D, displacement decreases. So it is taken as minus R cos theta minus of L square minus R square sin square theta 1 raised to power 1 by 2, that is square root of this term, that is L square minus R square sin square theta 1. Okay. So in this way, displacement of the follower is computed through this equation in terms of theta 1. Okay. And theta 1 is measured from 0 to theta 1. So theta 1 is measured anticlockwise from the position J to D. Clear? Okay. Next, to find the velocity. Definitely velocity is nothing but the rate of change of displacement, and differentiating the above equation with respect to time and then with respect to theta 1, we get the velocity as r into omega into sine theta 1 plus r sine 2 theta 1 upon 2 into L square minus R square sin square theta 1 raised to power 1 by 2, that is under root of this term, right? So this is the equation which gives us the velocity of follower when the roller moves on the surface of nodes from J to D. Actually, roller is moving from D to J, but we are measuring theta 1 from J to D. So I am saying from J to D. So at point J, theta 1 is 0, and at point D, theta 1 is equal, the angle turn is equal to theta 1, that is the maximum theta, right? So here velocity we have computed, we can compute by means of this formula. Now coming to acceleration, the acceleration of follower again can be computed by the rate of change of velocity with respect to time. So differentiating velocity with respect to time and thereby with respect to theta 1, we get another equation, and this equation gives us the acceleration of follower when it moves on the surface of nodes of the cam. Now here, since theta 1 is measured from top position of the roller, therefore for the roller to have contact at the apex of the nodes, that is at point H, then theta 1 is equal to 0, right? This already we have discussed. And for the roller to have contact where straight flank merges into nodes at point G, then theta 1 is equal to alpha minus phi, where alpha is the angle, semi-angle of ascent. Now this alpha is the semi-angle of ascent and phi is the angle turn during the motion of follower on the surface of flank. So theta 1 is always the difference of alpha and phi. So it cannot be greater than alpha, right? The velocity is 0 at point H and maximum at point G. The equation, if we see, then the velocity is 0 at point H as theta 1 is equal to 0. Sin theta 1 becomes 0 and velocity becomes 0, and it is maximum at theta 1, which is nothing but alpha minus phi. Then the acceleration is minimum at point H and maximum at point G. Okay. So these above analysis can be understood by means of the graph which is plotted here. So here the displacement, velocity and acceleration graphs are drawn for the angle theta when it is measured between 0 to alpha. Okay, so it is for the outstroke only. The graph shows the profile of displacement, velocity and acceleration when it when the cam turns to maximum angle alpha, and similar graphs can be obtained for the return stroke also. So here we can see that from the angle 0 to phi, this is the angle turn by the cam during the flank surface, right? And from phi to alpha on the nodes. So on the flank, if we see, the displacement is not rising with very high intensity at the beginning, so it starts with slow displacement, and at the end on the surface of flank, the displacement in between the small turn, displacement increases, right, on the surface of flank, and this displacement on the nose is quite deaccelerating. That is, we can say that the velocity is not increasing here. Here velocity has increased and it turns to slowly turns down. So this is the curve of the displacement during follower motion on the surface of line, and this is the curve traced by the follower on the surface of nose. If we see the velocity diagram, then for the angle phi, the acceleration increases as theta increases, and it attains maximum value when it reaches to phi. So theta, when theta reaches to phi, velocity is maximum, and velocity goes on decreasing with a quite straight profile as it moves from phi to alpha. So at point alpha, at point h on the surface of nose, velocity comes to 0. Here we can see that the displacement is going down, down, down and down, the rate of change of displacement. So theta turning, the angle turn is high and the displacement is low. Here the angle turn is low and the displacement is high. So here velocity increases up to this point, and from this point onward velocity decreases and it reaches to 0. And if we see the acceleration profile, then acceleration, if we see the acceleration increases at the start. This is the 0 line, and at the beginning only it has some acceleration at 0 position, and the acceleration increases and reaches to maximum position at angle phi, and at this position only the acceleration has the lowest value as it turns on the surface of nose. So this is sudden change in acceleration, and we can say that when the follower moves from the surface of flank to the surface of nose, it can observe sudden jerk at this position, and then acceleration increases and reaches to some negative value when it reaches to point H. So when angle turn by the cam is reaches to alpha. Okay, so this is the graph for displacement, this is the graph for velocity, and this is the graph for acceleration when follower moves on the surface of flank, straight flank and nose. Okay, so here I conclude the tangent cam with straight flank. Thank you. Now it will be interesting to understand the importance of the formulas which we have derived or seen before in computing the actual dimensions of cam for any application. So let us go through a problem which will enhance our knowledge in using the above formulae to find out the actual dimensions of cam for any application. So in this problem it is given that a cam with a symmetrical tangent cam operating a roller follower, the least radius of cam is 30 mm and roller radius is 17.5 mm. Now least radius of cam is 30 mm, so definitely this 30 mm is nothing but the base circle radius of cam, and this base circle radius, let us say this is R1. So R1 comes to us as 30, and the roller radius of follower is 17.5, so let us say R2 is equal to 17.5 mm. Now the angle of ascent is 75 degree and the total lift is 17.5 mm. So the maximum angle turn during ascent is given to us as 75 degree, that is alpha, and the value of total stroke during ascent is 17.5 mm. So total stroke or lift is given to us, and the speed of the camshaft is 600 rpm. Now it is desired to calculate 1. The principal dimensions of cam, and 2. The acceleration of follower at the beginning of the lift where straight flank merges into the circular nose and at the apex of the circular nose. So we need to find the acceleration at the beginning of the lift where the straight flank merges into the circular nose, that is at the position where the roller moves from flank to nose and at the apex. At three positions we need to find the acceleration. So assume that there is no dwell between the ascent and descent. So in between ascent and descent there is no dwell. It is given to us that there is no dwell. So let us start with the problem. So in this case, as far as cam profile is concerned, let us understand the shape of cam again. So it's a tangent cam with straight flank, so it has a base circle radius, it has a nose radius, and it has a distance of some distance between the center of base circle and center of nose, and all these computes the actual stroke of the cam. So total stroke is due to the distance between the two centers of, that is nothing but cam center and the center of nose and the radius of nose, and these two both are not given to us, and it is asked to find the actual dimensions of cam. So here we have given R1, that is base circle radius, we have given total stroke, that is 17.5 mm. The radius of roller is given to us as 17.5 mm. Angle turn is given to us as 75 degree, and the RPM is 600, so omega comes to us as 2.90 by 60, that is equal to 62.84 radian per second. Let us say small r be the distance between the two centers, and that is nothing but OK. Okay. So here r is equal to OK, that is distance between the two centers, that is cam center and nose center. R3 is the radius of nose, and let us say phi is the angle of contact of cam with straight flank. So this is the angle phi with the straight flank. So when it moves, when the roller moves from E to G, the angle turn is say phi. Okay, so it is the angle between OB and OD. So from the geometry, if we are interested to get the total stroke, we can say that total stroke should be equal to R plus R3, right? At point H, the follower will be at the highest position, and the total stroke should be equal to total strokes not should be equal to R plus R3, but these two are going to compute this stroke. So we can say that R plus R3, this distance, total distance, is equal to R1, that is nothing but the base circle radius, plus if we trace out this circle here, then this is the total distance which we are getting as lift. So this total lift plus the base circle radius should be equal to OH, right? Therefore, we can say that OH is equal to, OH can be measured in two ways. OH is equal to R plus R3, and that is also equal to R1 plus total lift. Therefore, we can say that R plus R3 is equal to R1 plus total lift, and in that way we get the value of R in terms of R3, putting the value of R1 and total lift which is given to us. So we get R, that is the distance between two centers, equal to 47.5 minus R3. Now we are interested to find the value of R3. If we compute the value of R3, we will get the value of R, right? So for that, what we do, we construct a rectangle. Now here D, G and E is clear to you, that is E is the beginning point and G is the end point when at the end of the straight line, right? So we draw extending this KG, we get point D. So the center of roller is moving from B to D on the surface of flank. If we join, we draw a rectangle BDKP here. So this is a rectangle. So here angle KPB is 90 degree, and in that case we can say that OE, this total distance OE, is equal to OP plus PE, right? OE plus PE. Now OE is nothing but the radius of cam, therefore we can say that OP, this small distance OP, is equal to R1, that is base circle radius, and now OPE, P is nothing but, this is the nose radius. This, in this rectangle if we see, this is also another rectangle, that is KPEG, right? So in this rectangle GK is equal to PE, and GK is nothing but R3, that is the nose radius, right? Therefore EP becomes nose radius, and therefore we can say that OP is equal to R1 minus R3, that is base circle radius minus nose radius. Therefore we get OP is equal to 30 minus R3. Okay. Now from the right angle triangle OKP, now we see into this right angle triangle OKP. So in this right angle triangle OKP, OP is equal to OK. Now this angle, if we see this angle, angle OPK, this is right angle, whereas the angle POK is nothing but the maximum angle of ascent, that is alpha, that is nothing but 75 degree. Therefore in terms of alpha, we can compute OP is equal to OK into cos alpha, right? That is, this is OP is adjacent to this angle alpha, therefore we can say OP is equal to OK cos alpha, and putting the value of OP as 30 minus R3 and OK as OK is nothing but small r, which we have computed here as 47.5 minus R3. So R3 gets cancelled as R3. The value of R3 comes to us as this cos 75 degree will go down here, and we can compute the value of R3 as 23.88. Okay, so if we take cos 75 in multiplication, then we will be able to find the value of R3, and R3 will come to us as 23.88. Now here we are become successful to find the value of R3. As we find the value of R3, we can find the value of R. So here R is the nose radius and comes to us as 47.5 minus R3, and that is nothing but 23.62 mm. So here from the triangle, here we become successful to find the value of R and find the value of R3. Then we are interested to find the value of phi, right? So phi is the angle turned during the surface of flank during the period when follower moves on the surface of flank. So tan phi is equal to dV by OB. So in this triangle, that is OBD, tan phi, tan is nothing but opposite upon adjacent, so it is BD upon OB, and that is also equal to KP upon OB. Now OB is equal to base circle radius plus follower radius, that is R1 plus R2, and OP is equal to OK, KP. KP is equal, this KP is equal to OK sin alpha, and therefore tan alpha comes to us, tan alpha can be equal to, therefore phi comes to us as 25.6 degree. Okay, so I have written here directly equal to tan alpha, but this value is nothing but tan phi comes to us as 25 degrees. So we can say that when the follower moves on the surface of flank, straight flank, the angle turn is equal to phi, and phi comes to us as 25.6 degree. So in this way we can find the basic dimensions of cam when we are knowing the actual lift and base circle radius of the cam. Also the angle turn should be known. So by knowing these three things, we can find the actual dimensions of cam. Now as we have the value of omega, we can find the acceleration by the formulae that we had seen earlier. So when at the beginning we know that acceleration is minimum and it is equal to, at the beginning of the lift, acceleration is minimum, and that acceleration is equal to omega square R1 plus R2, and that value comes to us as 187.6 meter per second square. Now second acceleration that we have given to find is at the position where straight flank merges into the circular nose, that is at point G. So at point G the acceleration is maximum, and on the straight flank acceleration is maximum, and by that formula we can find the maximum acceleration by putting the value of phi. Phi already we have found here, and by putting the value of phi we will be able to know the maximum value of acceleration. Now phi is the angle turn during this motion on the straight flank, right, and theta becomes phi. So the maximum acceleration is 303 meter per second square, or it is 303.800 mm per second square. Okay. Then acceleration of the follower at the apex of the circular nose. So at the apex we know that the angle theta 1 is 0. So we are measuring the angle theta. Now here we can see this is the total angle theta 1, and at the apex theta 1 is 0. So the formula to find the acceleration is already we had seen in the previous section. So looking into this formula, theta 1 is only the variable, and theta 1 comes to us as 0. So putting the value of theta 1 equal to 0, acceleration, and omega, we are knowing the value of omega, we are knowing the value of r. So by putting the value of omega and r, we get the, now in this equation we need to find the value of L. Now what is L? L is nothing but the distance between the center of node and the center of ruler. So L is equal to nothing but R3 plus R2, that can be found. So by finding the value of L, other terms are known. So by putting the value of L, theta 1, R, R2 and R3, we will be able to find the value of acceleration, and acceleration comes to us as 146.53 meter per second square when the follower is at point H, that is at apex. Okay, so here we complete this numerical to understand the importance of the previous formulae in finding the actual dimensions of cam and the actual acceleration of follower. Okay, so we end up